Hello, welcome to the first video which will focus on quadratic functions. And let us take a quick look at the two different forms that quadratic functions can appear. One is sometimes called the general form, which is y equals ax squared plus bx plus c, where a, b, and c are some constants or some numbers. The other one, which is sometimes called the vertex or the standard form in the textbooks, is y equals a times x minus h, it's written as a squared plus k, where hk is a vertex of the parabola. And there are some benefits to having this form of the parabola rather than the general form, which can allow us to quickly draw a graph of this function. So let us review a few things from college algebra. First of all, how do we graph this using the vertex form? Well, if we keep in mind how to draw y equals x squared, which is the parabola with vertex at the origin. This is the standard parabola which we will use. There are five things that we will need. One is, let's first figure out what's the sign of a. If a is negative, then we have something that's called reflection, which means the parabola will be upside down for the regular y equals x squared. Now, if a is positive, then it's facing up and there is no reflection. Also, we need to know how big a is. If, regardless of the sign, if a is bigger than 1, or absolute value of a is bigger than 1, then our parabola appears stretched vertically, which means the graph actually appears narrower than the original graph. Now, if a is less than 1, whether it's positive or negative, then we have a compression, which means the graph appears wider than the original y equals x squared compared. So we always compare to y equals x squared. So we could have a to be negative 5, for example. That means we'll have a reflection and the parabola will still be stretched because absolute value of negative 5 would be 5, which is bigger than 1. So we also have a couple of shifts. H right here corresponds to the horizontal shift, and generally there is a little reverse, it's actually the opposite of what you would expect. If it's negative in the original equation, which means h is actually positive, by the way we set it up, the graph shifts to the right if we have a minus right here. Now if we have a plus, we have the graph actually shifting to the left. And k, the vertical shift, is actually more straightforward. So if k is positive, we're shifting up. If k is negative, the shift is down. So let us take a look at the first example, y equals negative 2 times x minus 1 squared plus 3. Can we figure out all the necessary components to sketch a quick graph? And yes, we can. So let us take a look on the next page. So we know a was 2, actually it was negative 2, but we're going to need to be 2, and h is 1, and k equals 3. So yes, a is actually negative, so we're going to have both reflection about x-axis, a is negative, and it will be stretched because absolute value of a, well it's 2, is bigger than 1, and we are shifted 1 unit to the right because we had a negative in the original equation, and 3 units up. So here is what the sketch of the graph looks like. Here's our vertex, which should be at 1, 3. So it should be more like right here. And 1, 3. And now you can see the reflection. It's a little bit hard to see that it's actually stretched. And we don't know exactly where it crosses the x-axis or the y-axis, but it doesn't matter, we're just drawing the sketch for now. And in fact, that's why we're going to have other methods to figure out the x and y intercepts. So when we are given a graph in this form, which if you guys recall, that's a general form, we can do one of two things. We can either get it to be into the vertex form by completing the square. That's one way, and I believe we actually discussed there is a way to find the vertex directly, which means a would always be the coefficient of x squared. So that's pretty easy. So if we can find the vertex, we can actually write the vertex form fairly easily. But there are some benefits to knowing how to complete the square as well. So that's what we first write it in descending order, starting with x squared minus 6x plus 10. Then completing the square there are a couple of steps we need to do. First, we just isolate the square term and the x term and move the plus 10 outside of parentheses. Then what we want to do, it's described a little bit, it's based on the perfect squares. Notice we actually have two first terms of the expanded form. We have the a squared, which is x squared for us, right here. We have the minus 2ab, which actually is minus 6x. That's why, because we have twice of what we need to be able to figure out this 9, which we're actually filling in right here, what we need to do is to find the middle coefficient, we need to divide by 2. I usually call it b. So if we can find the b, we divide negative 6 by 2. Then what we actually fill in, we need to fill in the b squared right here. So b squared is 9, and that's how come we fill in the 9. But to keep the equation balanced, we need to also subtract 9 on the other side. That way the net effect is actually 0. So let us take a look at what happens. And there you go. Once we write it in this form, what we can do is we can compactify this as x. Notice this is the b that we found. That was negative 3. So we can use it here. So it's x minus 3 squared plus 1. Because the 10 minus 9 gives us 1. And there you go. And the vertex is actually 3, 1. And axis of symmetry, pardon me, axis of symmetry is actually x equals 3. It's always going through the x of the vertex. And we can even find intercepts in this form the same way. X equals 0, that's what we use to find y-intercepts. That's usually fairly simple. So 0, 10 is the y-intercept. And we can use y equals 0, which means we actually set the equation equal to 0 right here. And we can solve for x, for example, which does not work out here because if we subtract 1 from both sides, we actually have a square equals to negative 1, which we cannot have real roots, which means there are no x-intercepts in this case. So this is how the graph looks like, and it makes sense. There's no reflection, and the vertex is above x-axis, 3, 1. So we don't have x-intercepts, and y-intercept is way out there at 0, 10. And same kind of idea we can apply when a is bigger than 1, which in this case is 2. It's a little bit more challenging because what we have to do, this is not quite a perfect square yet. So whatever the a is, we got to factor it out. That's how come a is on the outside actually. So we factor 2 out, but we'll leave the 9, the constant term, all by itself. That's not affected. Then we can still find the b, negative 4 divided by 2. That's what we do right here. That's negative 2. And b squared would actually be 4. So it's always positive. So we fill in the 4 right here. However, because there is a 2 on the outside, we have to distribute it 2 times 4. That's how come we get 8. And that's why we subtract negative 8 on the outside. And again, let us simplify. X squared minus 4x plus 4 is actually x minus 2 squared. Remember the b we found? This is the a that's still outside. And 9 minus 8 happens to be 1. And that's it. So actually with a little bit of practice, it's only a couple of steps usually, unless we have fractions. That's why the benefit of defining the vertex this way, this is another way of graphing. I call it the 5-step method. If we can find A, B, and C, if your equation is in the descending order, x squared, x, and then the constant, then each one of those A, B, and C constants tells us something about the graph. For example, A tells us if it's positive or negative. It tells us whether reflection occurs. So if A is positive, it opens up. Negative, it opens down. That's where reflection occurs. This is how we find the vertex. X, this is what we need to remember. X equals to negative b over 2a. So this is actually would help us. And to find the y, we basically plug it back into the original equation. That's what the notation means in the function notation. We plug in the x back in the original equation, and that's how we find the y. And y-intercept is fairly simple. If we plug in 0 for the x, if we recall that all that would be left is c. So 0, c is the y-intercept. Now x-intercepts are a little bit more involved. Since the equation is equal to 0, we can use the quadratic formula or factor if it can be done easily. Or this right here helps us to check the discriminant. This part under the square root, b squared minus 4ac, because if it's positive, we do have two x-intercepts. So it is worth to actually find them by using quadratic formula. However, if it's 0, we get one x-intercept, and it's the vertex, which we already find, or we can find using the other method. So it doesn't make sense to use quadratic formula. So we actually stop right here. And of course, if it's negative, we don't get any x-intercepts as in the previous example. So we don't actually need to proceed any further. So number 1, the first case, is the only time we actually need to proceed with quadratic formula. So it can actually save us some time. So let's take a look. And the symmetry sometimes is helpful, particularly if you don't have x-intercepts. Then it helps to find another point to be able to graph. So here's a little example where it's y equals x squared minus 2x plus 4. So a is 1, b equals negative 2, c equals 4. So parabola opens up because a is positive. The vertex x happens to be 1. Notice negatives cancel. And f of 1, if you plug in 1 inside of the x, we get 3. So it's 1, 3. The y-intercept, if you guys recall, it's 0c, which was 4. So to find x-intercepts, we check the discriminant, and it happens to be negative. Careful with the signs. Make sure you plug them in correctly. But there are no x-intercepts, which kind of, when you start plotting, should make sense. So how do we finish the graph? Well, if here's the vertex, if we have axis of symmetry, if you guys recall, it actually goes through the vertex. Then we can actually easily find the symmetric point. See, if we have y-intercept at 0, 4, then how we find the symmetric point? On the other side of the symmetry, notice this point, let us actually write it, is 0, 4. Then on the other side, and here's the vertex, it's 1, 3. Notice how the distance from the y-intercept to the axis is actually 1 point, because it's 1, 3. That means also 1 unit away from the axis in the other direction, there should be the symmetric point, which is right here. And so we can actually graph, and hopefully your graph looks better. We can complete the graph of the parabola. So our symmetric point would actually be 2, comma 4. Notice it's